We're looking at polynomial functions today, so let's start out with our general form. F of x is equal to a sub n times x to the n power plus a sub n minus 1 times x to the n power. All this means is that the n is equal to the highest degree. Okay, and then this one would be n minus 1, so 1 less degree, and then 1 less and 1 less until we get down to our constant at the end. So an example would be like f of x is equal to x cubed plus 2x squared plus 3x plus 1. Your n value would be your degree, so n would be equal to 3. Okay, so we're going to look at even. So if I have a function like a mother function, like f of x equals x to the 4th power, or f of x equals x squared, or x to the 6th, those functions look like this. Okay, this would be like x squared. If I had a function like x to the 4th power, it basically looks the same, but we level out a little bit more. Okay, oh, that was a bad example. Okay, in the middle, we're going to level out and then shoot up faster than x squared. Okay, x to the 6 would level out even more and then shoot up faster. X to the 6. These are the characteristics of mother functions that have an even degree. So we are just, our mother function for a polynomial is just one term to the degree, not adding anything after that. Okay. We're going to look at odd mother functions. So x to the 5th, x to the 3rd, x to the 7th. We can see that their domain is all real numbers. The range is all real numbers. We intersect at 0, 0. It's an odd function, and it's always increasing. So it's going to look something like this. This, like a cube, okay? This would be like x cubed. We'll do x to the 5th power. In the center, between 1 and negative 1, it levels out and then shoots up faster. Levels out and then shoots down faster than x to the 3rd. Okay, there's one more. Okay, so x to the 7th would level out even more and then shoot up faster. So in between negative 1 and 1, it levels out and then it shoots up faster than the other functions with a lower degree. Okay, so we're going to look at n behaviors, and we first look at the leading coefficient. So as x moves without bound towards negative infinity and positive infinity, to the left and to the right, the graph of the polynomial, this just means the polynomial, let's go pink. Eventually, we say rises or falls, rises to infinity or falls to negative infinity. Okay, so use the term rises and falls here. Okay, if the leading coefficient, so first we're going to look at, odd degrees. So if the, like, x to the 3rd power, okay, so if the leading coefficient is positive and the graph falls to the left, the end rises to the right. So an example of this would be like positive. So I'm going to do ax to the n. So if my a is positive, we get 3 times x to the 5th power, let's say, we're going to rise on the right and fall on the left, okay? And then the next one, if the leading coefficient is negative, the graph will rise on the left and fall on the right. So it looks like this. Again, here's an example. So ax to the n, my leading coefficient is a. We're going to be like, negative 3x to the 5th power. Okay, that's what the n's look like. Next, if the leading coefficient is positive, the graph will rise and rise. So let's do an example. Ax to the n is y. Y is equal to 3x to the 4th power. The graph will rise and rise. Okay, if the leading coefficient is negative, the graph will fall and fall. So an example, y is equal to ax to the n. So my a needs to be negative, so like negative 2x squared. The graph falls and falls on the ends. Okay, so we use our leading coefficient test to tell us which direction the graph is going to, what direction the end behaviors of the graph are going to end up. All right, so try these and pause the video, try these, no calculator, okay? So we're just sketching the end behaviors. You don't have to do the middle part, okay? Oh wait, yes you do. You need to sketch the middle part, okay? All right, here we go. So -3 is my k value, so I'm going to go down 1, 2, 3. And then it's x to the 7th. My a value is 1, and that is positive or greater than 0. And my n value, my degree, is odd. Degree is odd. So I know that the ends are going to go up on the end. So I'm just going to sketch this in. It flattens out and then shoots up. So on the ends, I am rising on the right and falling on the left. Okay. The next one looks like it's going to be like a parabola but flattened out. I can see that my a is less than 0, which is negative, and my degree is 6, which is even. So the function is going to fall and fall, okay? And I can see this is my h value. We're going to move over 1, and then to flatten out and then fall. All right, zeros of a polynomial. We have a lot of names for zeros. They're super important. Okay, we have zeros, yes. Then we have x-intercepts. We have roots. We call them solutions. We can call them, we can pull out our factors like x minus a, and then we also label them as a comma 0 for my x-intercepts. For a polynomial of degree n, the function has at most n real numbers, so the same as your degree. And then the function has at most, for extrema, n minus 1 extrema. So let's do a little example. If I have y equals x cubed plus something plus something plus something, what is the most number of times your function can intersect the x-axis? Okay, so I'm just going to draw us a cube function, something like that. Okay, and the most number of times I can see here are like 1 2, 3. I can move the function, I can translate the function. I'll just do it. You can translate the function up and have 0 real roots, 1 real root, or 2 real roots. Let's see, 1 real root, 1 real root. Okay, but I'm never going to be able to have more than 3. How many extrema? So let's go ahead and write. This is a degree is equal to 3, which is my n. Okay, so I have a possibility of 3 real roots, no more. And then I have a possible 2 relative extrema, which is relative mins or maxes, no more. Okay, I can see my extrema, 1, 2. There's not going to be more bumps than that. All right, if the function is even degreed, this is the n is equal to 4. That's my degree. So no more than 4 real roots. And no more than n minus 1, which is 3. 3 relative extrema. Okay, here are our roots. 1, 2, 3, 4. And then my extrema, 1, 2, 3. Never going to have more bumps than that. All right. Find all the zeros of the function algebraically. You're going to do this on your paper, and then we're going to check all these answers. Here we go. I have, I'm going to factor out an x. So I have f of x is equal to x times x squared minus 2x minus 3. I'm going to big X this, negative 2 and negative 3. I multiply by negative 3 and add 1 to give me negative 2. So I have f of x is equal to x times x minus 3 times x plus 1. And since I'm looking for zeros, I can switch out my y with 0. So x times x minus 3 times x plus 1. I'm going to use zero product property. Any of these factors that equal 0, when I multiply, that will give me 0 in the end. So I'm going to split these up. X is equal to 0, x minus 3 is equal to 0, and x plus 1 is equal to 0. So I add 3. X is equal to 3 minus 1. X is equal to negative 1. So when x equals negative 1, I get a 0. When x is equal to 3, I get a 0. And when x is equal to 0, I get a 0. These should be my x-intercepts. Next. All right, g of x. I'm going to factor out a negative 2x squared times, see, I'm left with an x squared minus 1. Ooh, that looks like a difference of squares. The first value is squared, the second value is squared. Let's see. So whoa, crazy. Okay, my first value is a perfect square. My second value is a perfect square. They are separated by a minus. So I can use my difference of squares factoring, which is x plus 1 times x minus 1. G of x is equal to, we're in factored form now. So let's go ahead and substitute out a 0 for the y. Negative 2x squared times x plus 1 times x minus 1, and zero product property. So negative 2x squared is equal to 0. Then x plus 1 is equal to 0. And x minus 1 is equal to 0. I'm going to go ahead and solve here. X is equal to negative 1. That is one x-intercept. X is equal to 1. That is another x-intercept. And I see when I divide by negative 2, I get x squared is equal to 0. So x is also equal to 0. These are my three these are my 3 x-intercepts. All right, lastly, h of x is equal to x squared plus 1. I'm going to go ahead and, since this is our x term is a perfect square, I can go ahead and just swap out the 0 for y and go ahead and start solving for x. I'm going to subtract 1 to get -1 is equal to x squared, square root, and I get an imaginary root. And we're looking for real roots, so we don't have to worry about this. Think about what this looks like. Let's see, x squared plus 1. When the extrema turns, well, when the function is above the x-axis, basically, then we get imaginary roots. If the extrema turns without hitting the x-axis, then we're going to have imaginary roots in our graph. Okay, we're just going to go ahead and I want you to graph these in your calculator really quick and make sure your functions match. I can show you what they look like now that you've graphed them. I have something like this. 1, 2, 3. The graph looks something like that. Okay. This one I have roots at -1, 1, and 0. And it's a 4th degree polynomial, so it goes like this. Okay. Last rule. This is a long one, sorry. Okay, if we have a repeated 0, then whatever the k value is tells us what the graph is going to look like. Okay, so if the k value is odd, the graph will cross the x-axis or go through. Okay. If the k value is even, the graph will bounce. So for example, x plus, when I look at y is equal to x plus 3 to the 4th power and y times x minus 5 to the 3rd power, x minus 3, so I have roots here at x equals -3 and x is equal to 5. The degree for this factor is 4, which is even. And the degree for the second factor is 3, which is odd. So I'm going to go ahead and graph in -3 for my root and +5 for my other root. 3 and 5. The a value is positive. My a is positive, and the overall degree is 7 because it's 4 plus 3. So leading coefficient test says my a is greater than 0 and the overall degree is odd. So the graph is going to rise on the right, and then when it's odd, the arms go at different directions. So rise at the right and fall on the left. And then it's the degree at -3, the root of -3 is even. So the graph is going to bounce off the x-intercept. So it's going to come and touch the x-intercept and come back towards the negative side. Then when it comes to the root at 5, it is an odd degree multiplicity. So we're going to go through and connect to our end behavior. I forgot one thing. The repeated root, the degrees here, these are called multiplicities. Okay, so the degree of the factors is called the multiplicity. And that's that.